I did it myself with some friends, but I see I'm getting old.
You should feel younger.
Well, after that, not really. After all the pain that you feel.
Okay.
But I was annoyed by professionals, because I call them and they say, "Oh, we have no time," and maybe in June, and they say, "Oh, but you see, you need 3 people, or you will need a lift and this and that," and so at the end, I just did it myself, and
I see. I see.
it's a lot of work also, administrative work. I have to go to changing address and everything, so a lot of trouble.
I see. So what is the weather like?
Sorry?
What is the weather like?
Well, it's not so bad. We get some sun, so
Windy, cold.
Yeah, a bit cold for the season, but it's Belgium, so we're getting used to it. So how about in St. Petersburg?
Oh, in St. Petersburg, it was very good weather in the beginning of May, and now it is much worse. It is windy, it is cold, sometimes raining, and it is not pleasant for me. But it is bearable, because weather is variable here, this time of the year. It may be very hot and sunny, and it may be cold and raining. And June is usually better. June and July, they're better.
Unpredictable.
Not predictable, because we're at the seaside, you see, and well, you cannot say what will happen in the next several hours. It may be raining, it may be windy. Well, with your permission, we will wait for several minutes, yeah?
Sure, yeah, sure.
Yeah, then I will announce your talk, and then you will give your talk. Thank you very much for agreeing to give a talk for us. It is, I am sure it will be a pleasure.
Well, thank you for inviting me. I'm very pleased.
Just feel yourself in the state of permanent invitation. And in touch with Pavel Hansel?
Sorry?
Are you in touch with Pavel Hansel?
Oh, yes. So we are still working on creating neutron stars. So
very interesting. Yeah.
May I ask also, are you in touch with Mike?
Yes. Yeah, he's doing well. Still working as hard as before. He's actually pushing me to work on this pasta paper, and yeah, it's quite incredible.
So what do we have? So what do we have?
Very cool plot above you, Nicola.
Yeah.
At the bottom,
Yeah.
this nuclear chart, very exciting.
Yeah. So what shall we do? It's 5 minutes, yes?
We should start probably, right?
Yes, I think we can start now.
Yeah, I believe that we have. Yeah, I believe that we can start now. Nicola, you can try to share screen,
Yes.
perhaps.
Let me try that. So. Okay. Can you see the screen?
Yeah, very good. Everything is seen, so we can really start. And in the beginning, I will say a few words about our speaker because he didn't give us talk at our seminar. Nicolas Chamel, he was born in France in 1978, and his university education started in 1998 at the University of José Fourier in Grenoble, France. He studied there for 2 years and then moved to continue the university education to the United States. It was a special grant as far as I can understand. And for 2 years in 1999 to 2000, he was a student of University of California in San Diego. And in 2000, he got master degree in physics. It was again in Grenoble at Fourier University. And the next year, 2001, Nicolas got a master degree in theoretical physics, École Normale Supérieure in Paris in France. And then during 3 years, he worked on his PhD thesis. It was at Meudon Observatory, University Pierre and Marie Curie in Paris, under supervision of Brandon Carter, and the title of the PhD thesis was Entrainment in Neutron Star Crusts. It was defended with distinction in 2004, and after that, Nicolas got a postdoc position for 1 year at SAMC, working with Pavel Hansel, and then he decided probably to drift to Belgium, to Brussels. Institute of Astronomy and Astrophysics and Free University of Brussels. First he was a postdoc there, then a lecturer, research associate, and now I believe that he is having permanent position here. His main fields are compact stars, superfluidity, neutron star interiors, and he is mainly trying to construct nuclear density functionals for nuclear physics and nuclear astrophysics and test them against observations of neutron stars and against nuclear physics experiments. So he's very very actively working according to astrophysical database system. The number of publications during about 20 years is about 150, but I do not believe in these numbers because anytime when I open a volume, for instance, physical review or monthly notices, I always it is just always happens that I can find publications of Nicholas. Well, and for today, the subject of the talk is consistent model of dense matter, neutron stars against astrophysical observations. Please, Nicolas.
Well, thank you very much for this fairly complete introduction. So I will review essentially the developments that have been made in Brussels, and also with many different collaborators. So what is the challenge in trying to describe consistently the interior of a neutron star? In fact, well, I don't really like the word star. I think it's somewhat misleading, because if you think of the internal structure of a neutron star, it looks more like a planet with a solid crust, a mantle possibly, and a liquid core. So a rather complicated internal structure with quite different phases and a very huge range of densities, from a few grams per cubic centimeters at the surface in the atmosphere, down to several times the density found in the heaviest atomic nuclei. So the challenge is really to try to have models that are able to cover all these different layers in a consistent and unified way. So why is it important to have a consistent description? So this question actually has been addressed recently. For instance, in the work of Morgan Fortin and collaborators, who showed that depending on how the matching is done between different equations of state in the crust layers and in the core, which is a very common practice, then this can lead to substantial errors on the radius of neutron stars. So you can see, for instance, on these figures, curves corresponding to unified equations of state, or to the matching between different crust and core equation of state at different densities. And here is just the simplest possible matching, just gluing pressure versus density relations. And so the errors can be something like a few percent for the radius, but it's much more for the crust thickness on the right panel, where you can have errors of about 30%. Now, this is this leads also to errors for the tidal deformabilities, which are important quantities for
Nicolas,
waves.
probably we do not see your slides. We see the title only, so probably you shared a different window.
Let me see. Can you see now?
Yeah.
Yes,
now
it's okay.
Okay, maybe
yeah, now we see, and yeah,
good.
and probably you can make it full screen.
Maybe I would just keep like that. Can you see the?
Yeah, we see, but we see
Yes,
also these.
Perfectly.
Yeah, if I do full
some
screen,
PDF
then
instruments.
something. Let me try. Do you see the change of slide?
No. No. Probably then you share screen, you should select the window where is, so maybe you stop the share screen and share it again. And
okay. Sorry about that.
And select the window with the full screen presentation, maybe.
Maybe I should, or maybe the desktop. Let me try this. Because I shared the window before, but apparently this is what went wrong.
No, now we see.
No.
Okay. We see your calculations.
Many things.
Can you see the screen?
Oh, now it's yes. And can you try to? Oh, now it's perfect.
Okay, so it's just okay, sharing the desktop and not the window. Okay, sorry about that.
Yeah.
So here I was talking about the matching between different equations of state, and you can see here the impact on the mass radius curves depending on different matching prescription, different densities. So similarly, there is also some errors induced by the matching on the tidal deformabilities, as was shown recently by Ferreira and Providencia. And the errors can be about 20% for the log numbers for low mass neutron stars and 10% for the tidal deformability. So this is far from being negligible. It's still such kind of errors are usually not discussed in papers. So just people say that they are gluing equations of state. We don't really know how, but one should be aware of this kind of errors. And this is a reason for adopting unified and consistent equations of state. Now, I think another also important aspect regards the use of inconsistent microscopic inputs. And I think this is particularly true for the cooling, where there are many different parameters. Now, some of the parameters are, let's say, physical, like on the left panel, taken from this paper by Sasha Potekin and collaborators, where here the parameters is the composition of the heat blanketing envelopes, of the hot envelopes, which is a physical parameter, but there are also internal microscopic parameters, such as pairing gaps, and varying the pairing gaps changes obviously the cooling properties. Now, if we do not have consistent inputs, one has to pick equations of state, pairing gaps, and so on from different models. But in reality, if we use a single model, then all this degeneracy will disappear, and not all possible combinations will be allowed. So this is another motivation for us to try to provide all these inputs within a single microscopic framework. So here the outline of my talk. So I will first discuss how we describe dense matter and the constraints from laboratory experiments. If I have time, I will say also some words about the role of the magnetic field. And the second part, which will be shorter, I will then discuss astrophysical observations and what can be learned. So let's start with the internal constitution of a neutron star. So this is my single slide about the microscopic model, a single formula. So the approach we followed is the density functional theory. So this is a very generic framework which has been widely used in condensed matter physics and chemistry. And so essentially the ideas is to treat the particles, so here the nucleons, as somehow independent quasi-particles, but in a self-consistent field that are generated by all the particles. So it's not a mean field approximations, but the equations look like mean field. So it's not mean field because it's not perturbative developments. So here are the typical type of equations we are solving for stationary systems, where H is the single particle Hamiltonian, which in general contains itself various fields which are related to effective masses, potentials, and so on, depending on whether they are currents or whether the matter is spin polarized or not. And the delta is a potential describing the pairing between nucleons, which is responsible for superfluidity. And all these potentials depend themselves on the wave functions. So all these equations are actually highly nonlinear. Okay, so now the advantage of this approach is that it is very versatile. So this can be used to describe atomic nuclei, so finite systems, but also infinite nuclear matter. So in this way, we can use the same approach to describe the different layers of neutron stars. So in principle, the density functional is exact, and there are various theorems by Cohn, Sham, and many others that were extended to also to time-dependent cases. But of course, we do not know the exact functional. So in practice, for practical calculation, we still need to use some phenometrical functionals, but we can test whether the functionals are reliable or not by just comparing with existing data. Now, how can we quantify nuclear uncertainties? So if we look at infinite homogeneous nuclear matter, we can expand the energy per nucleon in terms of densities, but also in terms of asymmetry, so the difference between neutrons and protons. And in this way, we can introduce various parameters. And one of the most useful and relevant is the symmetry energy, which it itself can be expanded in terms of the density. And the two most important parameters are the symmetry energy coefficient J and the slope L, as we will see later. So we have developed a series of different functionals to try to span these uncertainties. And the goal is to then compare the predictions from these different functionals to astrophysical observations. So how we construct the functionals? We use essentially all available atomic mass measurements, but also measurements from nuclear charge radii. We also put constraints on the symmetry energy coefficient, because if we take values outside the range given here, then we cannot get good mass fit.
May I ask a question?
Sure, sure.
What about hyperons?
So we do not include hyperons so far, but this can be also included within the same framework.
Thank you.
This is for the perspective. So they could be included in the same framework, but so far we have restricted to the minimal neutron star model with only neutrons and protons. Yeah, thanks. So we use also data from ab initio calculations. So not only the equations of state, but also parent gaps and effective masses. And we ensure that there are no instabilities, spurious instabilities to spin and spin isospin fluctuations. So I will focus on the series basically 22, 26. So they were fitted to different representative neutron matter equations of state. So the famous APR equations of state, which are based on variational calculations. But we also consider diagrammatic calculations from Lee and Schultz, simply because these span the range of stiffness as predicted by various calculations. And the shaded area shows different kinds of calculations, quantum Monte Carlo calculations. And you can see that this indeed lies within this range. We also have compared to more recent calculations based on chiral effective field theories. This is also compatible with these new calculations at, as you can see here, at somewhat lower densities. So an important quantity is the symmetry energy, and there are various observables to constrain the symmetry energy. So they are shown here. for various densities. So the symbols represent values extracted from various properties of atomic nuclei, from their structure or for oscillations, resonances of nuclei. And the shaded areas represent constraints inferred from either heavy-ion collisions for the blue area, or neutron skins, or the electric dipole polarizability of LEM. And you can see that the predictions from the BSK functionals are all lie in rather good agreement with these constraints. So the main difference between these different functionals is the properties at higher densities that are relevant for the core of neutron stars, where here the differences are quite important, especially between BSK 26 and the others. So now let's apply these functionals to neutron stars. So first, let's start from the surface. At least from the surface, we expect to see to have iron, and this is corroborated by the identification of iron line from accretion disk around neutron stars in low mass X-ray binaries. So actually, from Earth, it is possible to probe the properties of iron, but for astrophysicists, this is not of so much interest, because even if we use nuclear explosions and laser-driven shockwave experiments, we can reach at most about 0.1 millimeter below the surface of a typical neutron star. So not so much useful for astrophysicists, but still within this tiny range, one expects to find very structural phase transitions. So how about deeper in the star? So a few tenths of centimeter below the surface, matter is already so compressed that atomic nuclei are crushed, and we have essentially bare nuclei in a gas of free electrons. So density is about 10 to the 4 gram per cubic centimeter, so dense plasmas. And as the density increases, then the composition of nuclei themselves can change. And the way to describe these denser layers, which represent the outer crust, is following these famous assumptions of cold catalyzed matter that was formulated by John Wheeler. So essentially a full thermodynamic equilibrium, which means also that we have pure layers made of single type of nuclei. We assume here that the electrons are essentially uniformly distributed, which is a very good approximation. And if we have a pure layers, then they are expected to be made of to consist of a perfect body-centered cubic lattice. So the only inputs here are atomic masses. So we can use measurements when they are available. Otherwise, we can calculate them using the density functional theory. Now, I would like to mention that, well, the traditional approach has been to minimize the Gibbs free energy for different pressures. And in fact, this was first shown by François Tondeur at ULB, but his paper is almost has been completely forgotten. And only a few weeks later, BPS did similar calculations. Now, the problem with this kind of approach is that you have to choose a pressure step small enough not to miss any layer. And this can be also rather costly, also nowadays not so much costly, because you have to minimize over the full range of possible nuclei, which is about of the order of 10,000. Now, at the time BPS did their calculation, they only considered 130 nuclei just for computing reasons. Now, recently, actually, I've shown that there is a very much faster way of calculating the composition, which is partly analytical. And instead of minimizing the Gibbs energy, it is much faster to just minimize the transition pressures between adjacent crustal layers. And these pressures can be actually obtained from analytical formulas. And so this is about 1 million times faster. That this could have been actually done already in the 70s with the computer available at that time. And this is very accurate. In fact, it could be even more accurate than the traditional approach, depending on which step it's chosen for the pressure. And so this kind of approach can be useful if one wants to run many calculations for statistical and studies and sensitivity analysis, for instance. So there's a computer code available here for those that are interested. Okay, so what are the predictions for such calculations? So down to about 200 meters, the composition is completely determined by existing measurements. As shown on this schematic picture, and at higher depths, one needs to rely on theoretical models. So a few years ago, there are recently measurements of exotic nuclei. Now this is very challenging, but even a single measurement can change the composition, and this was shown a few years ago with measurements of zinc 82. And the composition is very sensitive to very small change of masses. So even if existing measurements are improved, this can also change the composition. Now, deeper in the star, one has to rely on some theoretical models. And here are the predictions for the different series of functionals. And the different colors corresponds to different nuclei. So the first colors are the same simply because these are experimental measurements. So the difference only are below, let's say, about 300 meters, where there you can see some differences, though they are not dramatic. Now, what is the role of the symmetry energy there? Not very much, because the main effect here goes from nuclear structure more than the symmetry energy. Still, there is some small differences which can be easily explained. So the proton fraction, in particular, can be related to the symmetry energy, and these different functionals have different values of the symmetry energy. The higher symmetry energy is for BSK 22, and the lowest for BSK 25. But again, here the main effects come from nuclear structure. Here the equation of state. The differences here are again very small, and simply because the equation of state is determined by electrons. Okay, now you have noticed that there are some plateaus in these equations of state. Well, in principle, in these plateaus, there is a coexistence between different phases. But of course, in a neutron star, the pressure has to vary continuously, not the density, so that in fact we jump directly from one pure layer to another. But there might be another possibility to have mixed phases in between. And so this is something that was already studied long ago first by Freeman Dyson in '71, and later by Wheaton. And so we have revisited this possibility a few years ago by considering different types of compounds. And we focused on well, ordered crystalline compounds, because for the type of charge ratios that are expected, then disordered compounds seems to be disfavored. So here are some of the structure that we considered. So mainly cubic lattices, and only one hexagonal lattices. And so we try to see if such compounds could exist, but well, we were disappointed to see that in fact the only types of compound that could potentially exist are those with cesium chloride structure, but in a very tiny range of pressure. So this picture is really schematic and unrealistic. In reality, the range of pressures is something like 1 part in 10,000. So it's very very small and negligible.
And sorry, if the temperature, if this is too narrow interval, perhaps the temperature effects will be important and they will.
Yes, yes, indeed. And this is exactly what I wanted to discuss from the next slide. So indeed, this raises the questions, this small energy difference is really the question of our realistic the assumptions of cold catalyzed matter. And we know that neutron stars are born very hot. And so it might well be that actually the composition is frozen at some point when the neutron star cools down, simply due to the quenching of nuclear reactions. So we have explored this possibility with colleagues from Caen in France, and just simply assuming that matter is in full equilibrium at some temperatures, but then below some temperature, the composition is frozen. So it's not a full nuclear network calculation. It's just a full equilibrium down to some temperature. And here are the calculations. So the results for two different pressures, two different layers of the outer crust. And this shows the nuclear abundances in terms of the proton number Z for two different temperatures. The upper panel corresponds to the crystallization temperature, and the lower panel is just a fixed higher temperatures. So you can see that, well, in general, one can expect to have a distribution of nuclei, so different nuclear species could coexist. So the applications for that, this translates in some finite impurity factors, which is the variance of Z. Oh. Can you see my screen?
Oh. Now I see you.
Okay, there's something.
But not your presentation.
Sorry. Okay, I know. Sorry about that.
Yeah.
So here the impurity factor corresponding to the results shown previously. And one can see that there are actually layers, an alternation of layers, which are impure and pure. And as was recently also studied by Potekin and Chabrier, this has implications for the thermal and electrical properties of the crust, and therefore also for the cooling. But potentially this means that we can also calculate this parameter consistently.
Mm-hmm.
So in a created crust, there might be there's potentially more possibility to form compounds, and there's also something that we looked at, focusing only on cubic compounds. And here there are indeed more possibilities, but much work is needed to see whether such compounds actually form in the star. Here it was just thermodynamic stability, but one should really look whether they are actually formed. But this is, I think, potentially an interesting subject of research. Okay, maybe I will skip this part. So at some point, nuclei become unstable against neutron emissions, and this marked the transitions to the inner crust. And there, the way to treat the inner crust, we use fast approximations to the density functional theory, which is semi-classical, but which includes also shell effects and pairing perturbatively. Now we only include proton corrections, not neutron shell effect, because they're expected to be, and they were shown to be much smaller. And this approach has been also recently followed by other groups, and for instance by Alessandro Pastore at York University, who found actually a very similar results from what we obtained, and he also made a comparison between the full HLB calculations and this semi-classical approach, and he showed that this approach is indeed quite reliable. So the interesting thing in the inner crust is that the ordinary magic numbers for atomic nuclei, they change, and we get a different numbers. So in particular, z equals 28 disappears, and new numbers appear, like z equals 40. And this can be easily explained just by the fact that spin-orbit coupling is much weaker in this context, simply because the density gradients are much smaller. The matter is not the gradients are much weaker. So here are the compositions for these different models, and you can see plateaus corresponds to this magic z numbers, and the dotted lines show the results when shell effects are neglected. So here shell effects play a very important role for the composition. It is negligible for the equation of state, but not for the composition. So here shows the influence of the symmetry energy on the proton fraction. And there's again a hierarchy between the different models, which can be simply explained by the different values of the different behaviors of the symmetry energy. And similarly, if we look at the pressure versus density, the different behaviors can be also again explained by the different behaviors of symmetry energy, remembering that this is here the slope of the symmetry energy that is important for the pressure. So as can be done for the outer crust, we can also look at thermal effects, what thermal corrections can do for the composition, and this was done by the Kahn's group, in particular by Thomas Caro in his PhD thesis, who essentially used the fitted to BSK24. And they found in this way that indeed one obtained a distribution of nuclei centered around z equals 40 in this case. So this is also something that to keep in mind, that in reality there is a full distribution of nuclei, and so one should be also careful with these cold catalyzed matter calculations. And so one can also predict there the impurity factors. So I stress here that there is no shell effect in these calculations, and so that's why there is the impurity factor does not exhibit any peaks but only smooth curves. So all these parameters can again be calculated consistently within the same approach. So we can also here explain again the different proton fractions.
Just a moment, may I ask a question regarding the previous slide?
Yes, sure.
Yeah, this kink of the blue curve in the upper right corner. What?
Yes.
Yeah. What?
I think it's just a numerical noise there.
Sorry.
I don't think this is. You have good eyes. Yeah, I think it's just a numerical noise. Yeah. No. Okay, so the proton fractions can be again related to the symmetry energies, can be easily explained. And the important point here is that the proton fractions can be actually fairly high. So in the core of neutron stars, this can be about 30 or 40% depending on the model. So one should be careful with statements that proton fraction is 10%, which we can see in many papers. Depending on the models, it can be very much higher, and in fact not far from symmetric nuclear matter. Okay, so when we go down to still higher densities, one can have exotic configurations, these nuclear pastas. So we have recently also explored this possibility ignoring shell effects. And we found that there's indeed a sequence of shapes like cylinders, plates, and then homogeneous matter, as predicted by the simple liquid drop model. So this roughly coincide with the transition density roughly coincide with this liquid drop criteria. Now one should be careful, because if we compare results including shell effects for spherical configurations, then the sequence may change. So there is a question of shell effect should be further investigated, and there is ongoing work on these directions. Also, we found that proton drip is disfavored by pastas if they are included. But in all cases, the equation of state is essentially the same. So only the composition of the structure changes when pastas are allowed. Now, if we look now at the whole star, here is a plot of the adiabatic index throughout the whole density range from the surface to the core of the star. And the message here is, well, be careful with parametrization using polytropes, because the index can change quite a lot. Even if you only focus on the core, the changes is quite significant. So at least one should use different polytropes in different regions of the star if one wants to use such parametrization. Okay, how about magnetic fields? I'm not sure I have much time, so maybe I will go quickly through this part. So the magnetic field can also change the equation of state and the composition. So this has been studied by various groups. So in particular on the surface, the equation of state, the surface can be condensed. So instead of having an atmosphere, one can have a solid surface. And there was discussions some years ago with this object, this star, which exhibit an almost a perfect black body spectrum. And then it was speculated that, well, maybe this is an indication that the strong magnetic field, so that the surface is actually condensed. And there has been indeed evidence for a stronger magnetic field from polarimetry measurements reported by Mignani and collaborators. Now at higher densities, so when we have a plasma, with free electrons, relativistic electrons, then again the motion of electrons is quantized. And in fact, this was first shown not by Landau, but by Isaac Rabi in a paper which is essentially completely unknown and ignored for some reason. But he derived the general expressions for relativistic electron gas in magnetic field. And in the table shows how many levels of field for different values of the magnetic field in terms of the typical this 4.4 × 10⁻13 Gauss. So depending on how high the magnetic field, the equation of state and the composition can change. And here is the summary showing that some elements can disappear, and while others can appear. And even if the composition does not change, the transition density varies with the magnetic field, exhibiting typical oscillations. Now these oscillations corresponds to different filling of the electron levels. This can be also seen at the neutron drip. And in fact, all these different oscillations are somehow universal. So if we scale the different curves to the same point without magnetic field, then they essentially all match together. The small differences you can see actually comes from the electrostatic corrections, which themselves depends on the magnetic field, but these corrections is small, so the curves are essentially universal. And again, as can be done without magnetic field, when the magnetic field is included, we can also speed up the calculations using the analytical approach that I discussed previously. And we can also have, in this case, analytical formula. And the gain in this case is about 10,000. But this can be much more because the calculations in principle have to be repeated for various values of the magnetic field. So, so this can be useful to follow this this more recent approach, and there's a computer code to try for yourself. Here show the results for the inner crust, where the composition also changes. Also, the changes are somehow more erratic for the compositions, because the differences are very small between different configurations. So it is also more difficult to obtain reliably the composition. So this could be also some noise. This is not excluded. But for the equation of state, the effect here is much less important, and the equation of state smoothly merge with that without a magnetic field. And essentially in the core of the star, the effect is negligible for, let's say, a magnetic field of order 10 to 17 Gauss. Okay, so I've taken a lot of time, so let me go to observations. Well, the first kind of constraint we can get is just from the fact that depending on the proton fraction in the core, the fast direct Kerr cooling can be allowed or not, as you well know. And in particular, among these different series, BSK26 is the only model which do not allow the direct Kerr process. And this is not supported by observations, and in particular by observations of some accreting neutron stars in quiescence, and also from transiently accreting neutron stars. So BSK26 is ruled out by this criterion. Now BSK22 predicts a very low mass for the direct Kerr process, but well, the direct Kerr process could also be suppressed by superfluidity, so it's hard to conclude for this case. Now, how about other observations? And recently there has been in particular observations by NICER and XMM Newton regarding the most massive pulsar known, PSR J0740, for which both the mass and the radius have been measured. And here I show the results from two different groups, for which the analysis is different, so the predictions are not exactly the same. And interestingly, one can see that again BSK26 is ruled out by these completely different kinds of observations. So at least there is a consistency in these constraints. But all the other models remain consistent. There has been also observations of less massive pulsars, but all models are consistent with this less massive. So that's why I have not shown on this diagram. And well, as you know, we can also get information from gravitational waves since 2017. And this is particularly interesting because then we can really probe the interior of the star down to the center. And by simply analyzing the shape of the signal, we can identify well, different phase of the in spiral and the major, and learn also about the internal structure. And in particular, in 2017, LIGO and Virgo detectors observed the in spiral of two neutron stars. And during this in spiral phase, then we can learn about tidal deformations. And these tidal deformations are characterized by these so-called love numbers, which can be also expressed in terms of dimensionless tidal deformability coefficients. And the important thing here to see is that there is factors involving the radius to the power 5. So the radius appears in this formula, and this is actually very important. So what are the predictions for the BSK functionals? For the tidal...
May I ask
yes, sure.
Question to this brown circle, what does it mean?
I think it's just, well, this is a very schematic picture. So I think it's just to illustrate the inside and the outside of the star. So it is a space-time inside the star or outside the deformed star. So you can see above these blue blobs, which represent the tidally deformed neutron star, deformed by the companion. Yeah. So the green spheres represent the external, let's say, gravitational field, which induces tidal deformations of the blue of the space-time around the blue the star that is studied.
Thank you.
So, but it's just a schematic picture. So.
Yeah, I see.
So here are the predictions for the different functionals. So if we compare, in particular, BSK 22, 24, 25, then what varies is the symmetry energy between the different models, and especially the slope of the symmetry energy. And this follows, well, roughly a correlation that have been published by various authors. So there's a strong correlations between lambda and the radius in itself is correlated with the slope of the symmetry energy. So here we also observe this kind of correlations, but these correlations are not very precise. As you can see, depending on which relations you use, there is some substantial differences. How about the love numbers? Now, interestingly, if we look more closely at these coefficients, we can see that actually the symmetry energy has no effect on the love numbers. So they are the curves are essentially the same. So this means that the differences that are seen in the tidal deformability comes mainly from the dependence on the radius. So if you remember, the lambda is proportional to the love number times the radius to the power 5. So the symmetry energy only enters through the radius. So the main parameter that governs the love number is in fact the stiffness of the neutron matter equation of state. And to better see this effect, we considered an older functional, BSK 19, which is a very soft equation of state. And you can see here that there are clear differences between these different models, which correspond to different degree of stiffness of the equation of state, from the softest one, BSK 19, to the stiffest BSK 24. How about the role of the crust? So there has been a few studies trying to assess the importance of the crust, but with somehow contradictory conclusions. And this mainly stems from the fact that the approach that were followed were not consistent. So for instance, in one case, the authors use polytropic interpolations for the inner crust, and they simply varied the polytropic index. In another case, they simply extrapolated the equation of state for the core. So they extrapolated to lower densities. And in another study, they just matched a different equation of state. So part of the deviations are actually due simply to the matching or to the use of inconsistent equations of state. So we try to understand the role of the crust by using unified equations of state. And what we did, we compared two different cases. So the unified equation of state with the crust and a unified equation of state with homogeneous matter throughout all the star. Of course, this is unrealistic because we know that there is a crust at the densities below about half normal nuclear density. But the idea was just to see what happens if we compare homogeneous matter with a realistic neutron star. And here are the results. And you can see that, well, the crust in this sense plays a very important role for the radius of a neutron star, as expected, but also for the love number. But this dependence, these changes on the love numbers, it essentially is due to the change of radius. And this means that, in fact, we can predict these changes from actually analytical formula. And we've given formula in this paper. Now, if we look at the tidal deformability lambda, which is actually what is observed, the changes are actually quite small, is less than 1%. And this again comes from the fact that the changes in the love number K2 is compensated by the changes in the radius. But still, it was argued in this paper by Gamba and collaborators that the crust may still lead to systematic errors on the radii that are inferred from the analysis of the gravitational wave signal. So this is still important to use a unified equation of state and to treat the crust carefully. Now, in this comparison, there is no effects of elasticity. This has been studied by different groups, and their conclusions is that the effect of elasticity is actually negligibly small, is something like 1 part in 10 to the 8. So it's much smaller than the errors due to matching of crust and core equations of state. So as I mentioned, and as you all know, there were these famous observations of neutron star mergers in 2017, and from that, the LIGO-Virgo collaboration could infer the tidal deformabilities of the stars. And here are the results from the LIGO-Virgo collaborations, and added on top the predictions from the different BSK functionals, and the different the colored curves corresponds to predictions using different analysis, so different treatments of the gravitational wave signal. And the black curves corresponds to the predictions for the BSK functionals. Now, interestingly, this is the softest equation of state, the BSK 26, which seems to be favored by the gravitational wave signal alone. And on the contrary, BSK 22, which is the stiffest, seems to be well, marginally compatible, if not ruled out. If we look at the older series where we have BSK 19, which is even softer, it is in even apparently better agreement with this gravitational wave data alone. And interestingly, this very soft equation of state, there are also evidence from avion collisions that the equation of state is soft, at least at intermediate densities. One should remember here that the merging neutron stars, they are not very massive. They are masses around 1.4 solar masses. So the central density is not very high in these stars. So this is also something to keep in mind. Now, if we look at the radii that were inferred again by the LIGO-Virgo collaborations, from their analysis. Again, there are two different analyses depending on whether they used universal relations or parameterized equations of state. So there are different boxes corresponds to these different predictions. And we see that again, this data seems to favor with the soft equations of state, and at least from the gravitational wave data alone, it's difficult to conclude and to rule out models. Maybe BSK22 is, one could say, is maybe marginally compatible depending on the analysis. Now one can get more information by looking from the electromagnetic counterparts of the merger, and in particular the fact that there was a rather large amount of ejected material, up to 0.05 solar masses, suggest, when we compare to numerical simulations, that actually the two neutron stars did not promptly collapse to a black hole, but went through hypermassive neutron stars for a few milliseconds. And just this simple fact can allow us to draw, to have some more constraints on the neutron star structure. This was discussed by different groups, for instance, by Boswein et al. And Köpperl et al. And the reason is that whether the stars collapse promptly or not depend on the total mass of the system. If the total mass of the two stars exceed some threshold value, then there is a prompt collapse. Otherwise it goes through the hypermassive neutron star stage. And using empirical relations that were obtained from numerical simulations, these authors could obtain lower limit on the radius of a neutron star. And using similar arguments, they could also obtain estimates for the maximum mass, the range of possible maximum masses for neutron stars, and this is represented by the yellow area on this diagram. And this has been shown by various groups, so there are many references which can be found in the paper cited below. So from this diagram, well, we can see that, well, BSK19 is ruled out, but this was already known because it fails to reproduce two solar mass neutron stars. But these electromagnetic observations disfavor soft equations of state, such as BSK19 for even for not so massive neutron stars like 1.4 solar mass neutron star. So these observations are actually more constraining than the gravitational wave data alone. So they favor the stiff equation of state, as I said. Now, in principle, the star can also have higher deformation.
Excuse me, may I ask you a question about the previous slide?
Yes, sure.
I would imagine that the matter, when you merge two neutron stars, will be very hot. And so
Yes.
the effect of temperature should be important. But these equations of state are zero temperature equations of state, right?
Yes, exactly. Yes, exactly.
Is there a logical problem, you know, that you that you consider high temperature matter and try to somehow restrict zero temperature equation of state?
Well, of course, ultimately one should use finite temperature equations of state. I fully agree. So one indeed should be careful. Maybe for ruling out completely some models, one should also keep in mind that that these are zero temperature calculations. Now, the problem also is that all the constraints they are also obtained using, well, in some cases, some finite temperature equation of state, but where the finite temperature is also not fully self-consistently implemented. So, so it's clear that one should look further at these dependencies and the finite temperature corrections. The temperature might well be several tenths of MeV during the merger. So this is some things to keep in mind. But I think it is mostly important for the merger and post-merger phase, and less for the in-spiral. And the LIGO-VIRGO observations could mainly see the in-spiral phase, not the merger and the post-merger phase. But so I believe that for the in-spiral, this is still a reasonable approximation. But for the post-merger phase, then one should clearly use the finite temperature equations of state. Yes.
I agree. But this is this slide is about post-merger, right? Is when you have this hypermassive.
Well, yes and no, because as I mentioned, they used also some. They made use of empirical relations, which are based, on zero temperature equations of state. So, yeah, I would say it's not so clear. It's not so clear. But I agree that one should be careful with this constraint. But in any case, these constraints, I mean, for the constraint of the radius, they are lower limit. So, and the range of expected masses is rather large, and I do not expect that the temperature will increase the maximum mass below 2.5 solar masses. So, so for these specific constraints, I do not think that thermal corrections would drastically change the conclusions. But in principle, one should indeed use finite temperature equations of state.
Thank you. So
in principle, there could be also higher order multiples, not just the log number K2, L equal 2, but they can be also higher order. And not only what is called gravitoelectric, which means even parity, but there could be also gravitomagnetic perturbations, which are related to mass, to currents induced inside the star, and these are specific relativistic effects. And nowadays, the most realistic gravitational waveform approximants, they do include some of these higher order log numbers, in particular K3 and K4. And in principle, one should also, for consistency, include the gravitomagnetic tidal log numbers, because they enter at similar perturbative orders. So we have also looked at these log numbers. So we have calculated these log numbers for these different BSK, and essentially the conclusions are very similar to what we found for K2, at least for K3, K4, and we calculated up to L equals 5. Now for the magnetic log numbers, the situation is a bit more complicated because this depends actually on the fluid motions. So the conclusions can be different whether one considers static star, which is not very realistic, or for instance, rotational fluid motions. Then the log numbers are not only quantitatively different, but also qualitatively different because they the change of sign. So this could be also interesting to measure these coefficients, because this way we could also learn about the fluid motions inside the star. So we have calculated all these coefficients. They are available for all the BSK functionals. But okay, I have not much time to discuss more here. So let me go now to the conclusions. So we have constructed all this series of unified and thermodynamically consistent equations of state, and we are very also thankful to Sasha Potekin for having made fits of equation of state and compositions and all these Fortran routines that are now publicly available. So when you compare these functionals to observations, we have seen that very soft symmetry energies are ruled out by the cooling, but also by a nicer and XMM Newton observation. This is particularly the case for BSK 26, which is too soft. And on the other hand, stiff symmetry energy is disfavored by gravitational wave data alone. So there seems to be some tension here, but one also has to remember that we are probing here also different densities. So one also should be careful there. Now I haven't said anything about superfluid properties, but this is also something that we are trying to calculate, and in particular we are currently calculating pairing gaps consistently with the equation of state for the BSK, but also entrainment parameters. We also plan to include exotica, as was raised before, and hyperons, which are mainly relevant for massive stars. So I mean, the minimal model has been discussed will not be ruled out. It's still relevant, I think, for not too massive neutron stars. And of course, one should also include finite temperatures and allow for nuclear full distribution of nuclei in the outer and inner crust. So our long-term objective is really to try to provide all the necessary microscopic ingredients for numerical simulations of neutron stars consistently within the same scheme, and spanning the range of uncertainties from nuclear laboratory experiments. But well, we are still far from this goal, but we are progressing slowly, but hopefully there will be results for at least for pairing gaps rather soon. So thank you for your attention, and I also would like to thank the collaborators who also are involved in this project. So thank you very much, and sorry for all the trouble and technical issues.
Thank you very much, Nicola. That's very impressive. Thank you. Well, now I think we have time for questions. So please, are there any questions, comments?
May I ask a question?
Of course, Dennis.
The previous slide, Nicola, the symmetry energy. Are there any theoretical or microscopic calculations of the symmetry energy which you can guide or restrict through this ruling out soft symmetry energy, stiff symmetry energy, and so on?
Yes, there are many body calculations, but the problem is that these calculations are not very reliable. And the reason that to calculate the symmetry energy, so it is essentially the difference in energy between symmetric nuclear matter and pure neutron matter. And pure neutron matter, the calculations are quite reliable and the uncertainties are rather small, but this is not so much for the symmetric nuclear matter, for reason that the interactions in this case is more complicated, and the Pauli principle also does not act as it is for neutron matter. So the uncertainties are larger for symmetric nuclear matter. And it has been, I mean, also an issue in the 1950s, that even the saturation density, the equilibrium density in symmetric nuclear matter is not reproduced by microscopic approaches, or one has to introduce three-body interactions which are partly fitted to reproduce this point, or so the saturation density is quite uncertain. So one should be very careful when looking in the literature because generally people give the values of the symmetry energies they found, but they do not give the density at which the symmetry energy was calculated. And so if you remember that, the equation of state for symmetric nuclear matter, it's essentially a parabola. So this means that if you change a bit the density from the equilibrium value, from the bottom of the parabola, this can yield, well, significant differences on the energy. So it's difficult to compare microscopic calculations because usually the density is not given. So one is comparing peer and apples because you do not know if the density is the same. So that's why we do not use microscopic calculations for the symmetry energy, but they are very tight constraint, as I showed, or maybe this disappeared in these technical issues, but there are some rather tight constraints from just experiments. So this is shown here. So this is the density dependence of the symmetry energy from essentially zero density to about the equilibrium saturation normal density, 0.16 nucleons per cubic Fermi. And these are data extracted from either avion collisions or neutron skin in atomic nuclei or vibrations of atomic nuclei. And so you can see that they are rather tight constraint there. So the main uncertainty is usually at higher densities, and there it's still very uncertain. So the main uncertainties goes here at high densities.
So basically, microphysics is not very well developed at this moment, and they cannot use these observational results that the symmetry energy is neither soft nor stiff.
Yes, it's difficult to answer.
Okay.
Because, for instance, these recent effective field theory approaches, they are essentially limited to densities below about 0.2, 0.3 nucleons per cubic Fermi. So you cannot use this kind of ab initio, let's say, approaches to probe the symmetry energy in the core of neutron stars. So, but we have neutron stars, so, and we have observations. So this is a motivation. We can use neutron stars as a laboratory to probe the symmetry energy. Of course, we can also use avion collisions, but then the interpretations is very tricky and model dependent. So there are some constraints from avion collisions, but one should also be careful there because there are lots of model assumptions also behind. So
I see. Thanks.
Okay, more questions? Well, may I ask a question? Well, please.
I would like to ask about, you mentioned a consistent approach for pairing nuclear properties. What type of pairing are you using at the moment in your function now, and what could be the improvement?
So could you repeat your questions? You mean predictions for?
You mentioned in your conclusion, you mentioned that you are aiming at consistent approach to the pairing properties, if I'm correct.
Oh, yes, yes.
So the question is, what kind of pairing are you using in the recent version of your function?
Okay. Yes.
And what improvement are you considering?
Yeah, so for the pairing, so we construct, so we use local pairing functionals, and the pairing functional is constructed so as to reproduce microscopic calculations in neutron matter and in symmetric nuclear matter, or the whole density range, not just one point, but over the whole density. And then we use these functionals to calculate atomic nuclei, and so this is constrained by microscopic calculations of pairing gaps, essentially diagrammatic calculations of pairing gaps. So we still have to interpolate, because these calculations exist only for pure neutron matter and symmetric nuclear matter. And of course, for atomic nuclei, we need the gaps for arbitrary composition. So we just then use some interpolation, which is completely ad hoc, because we do not know how to constrain that. So we are pushing nuclear physicists, our colleagues, to calculate pairing gaps in asymmetric nuclear matter, but it turns out to be quite difficult, quite challenging. So.
Okay, my point is that you might have a problem for near drip line nuclei.
So in the late, yeah, sorry, I forgot to mention. So in the latest series that we of functionals, we also added an additional terms to this functional, which is proportional to the gradient of the density, which is phenomenological. And in this way, when you apply the functionals to homogeneous matter, then we reproduce the microscopic pairing gaps. But when we apply then these functionals to nuclei, we can account in a phenomenological way for contributions due to surface collective modes and finite size effects through the gradient terms. And this terms is fitted to atomic masses and radii and so on.
Yeah, I'm very pleased to hear that you are using the so-called science functional, which we developed in the Kurchatov Institute 30 years ago. Thank you.
Okay, more questions? Well, may I ask a question?
Yes, sure.
Nicola? Yeah.
Yes, sure.
What is your vision of hyperon problem here? Because it is additional complication. There are so many, well, problems here and now hyperons. Well, this will be, well, what is your opinion? Will it be possible to save, so to speak, hyperons in neutron stars?
Well, yes, there are different ways of saving hyperons. Well, as was shown by some groups, if you allow for other phase transition at still higher densities, like quark phase, with a stiff enough equation of state, then you can save the hyperons. But I mean, we just focused on this minimal model because then it starts to be quite speculative. The quark equation of state is not very well known. We not know where are the transition densities and so on. So this adds additional uncertainties to the model. So our motivation here was first to see what we can predict with the minimal model. It's like for the cooling, this minimal cooling paradigm. If we cannot explain some observation with the minimal cooling paradigm or with the minimal model, then we will introduce, exotic hyperons or something else. But with hyperons well, fortunately, there are more and more data on hypernuclei and also microscopic calculations. But it still remained very, very uncertain, and so I don't have a clear view on hyperons. And the idea that when I mention exotica in the perspective is just to consider different possibilities and then to compare the predictions from these different scenarios against astrophysical observation to see which one is favored or not. but it's rather difficult to say. From general considerations, at least we expect to see hyperons at about 2 or 3 times the density, nuclear saturation density. But this transition also itself depends on the interactions between hyperons, which is not so much well known. And so, if you were to play with repulsive interactions between hyperon, then you can also shift. You can shift the transition density to much higher densities, and this is actually also considered by some authors, where they solve the hyperon puzzle by simply making the hyperon disappear from the star. So. So yeah, I don't have a clear view at this time. We know that they exist and that they probably should be found in the core of neutron stars, but where exactly and how stiff is the equation of state, and it's still fairly uncertain.
Okay, thank you very much.
I have a question actually.
Please.
Yeah. Okay, so Nikolai, thank you very much for an interesting talk. I have a question. So if I'm correct that so all your functionals at high density region, you feed some of the parameters to the results of some microscopic calculations, right?
Yes.
And
yes.
Actually, right. And so, for instance, here in Lee and Schulze, you cite two models, but there are many calculations with a quite large uncertainties at this high density region, these microscopic things. Even in this Lee and Schulze paper, the difference in energy at high density is quite large for different models. So my question is, how do you select which of these models, microscopic models, results available on the market to use for your functional at high density?
Well, initially, essentially, we selected the equations of state. Well, we first chose APR because this is one of the most popular equations of state. But we also selected the equations of state that actually span the available range. So we picked the one from Lee and Schulze because this is among the stiffest that we could find in the literature. Of course, there are many calculations, but I would say that the one we selected more or less span the range of equations of state, and this is also consistent with more recent calculations that were, as I mentioned, that were performed by different groups following this ab initio approaches, and these still lie within this range. Now, in the time when we started these fits, we also considered much softer equation of state, BSK 19, but then we just ruled out this model simply because the equation of state cannot reproduce to solar mass neutron stars. So there are calculations with even softer equation of state, but then you cannot explain massive neutron star. So if you take BSK 19 up to BSK 22, let's say, then essentially this spans the existing range of available calculations.
Right, but considering the uncertainty at high density for these microscopic calculations, why do you need at all to rely on them, of any of these models? So you have 150 MeV easily at one.
Yes, well, because we also the reason why we considered in particular this Lee and Schulze models, because the same diagrammatic perturbative approach was followed to calculate other quantities, not just the equation of state, but to calculate effective masses and parent gaps, as I mentioned. So we tried to also be consistent, not fitting effective masses from one paper, parent gaps from another. So we tried to construct the functionals by using consistent microscopic calculations. So that was the reason. And at the time when we did these fits, there was no only these calculations provided other inputs than just the equation of state. So that was the reason for selecting this particular Lee and Schulz calculations results.
May I also add some remark to this issue?
Yes, yes, please.
In fact, consideration of another microscopic calculations, such as in BSK 26, was also done, but it leads to, as you have shown, it leads to well, absence of direct Urca processes. That is another. I mean, some one can try other parameterizations, but when taking into account all the wealth of data from different fields, it turns out that this present choice seems to be most reasonable for use in modeling. Am I right?
Yes, indeed. And again, this, I think we can test also the reliability of these functionals.
I believe that this
prediction.
choice is not the stiffest, right? You can.
No, yeah, BSK 26 is not is the softer. This is the softest on this picture.
Yeah, right. I mean that the current choice, like Lee and Schulz, this one, it's not the, I think, not the stiffest. You can use something which like give higher energy. So then you will get even better constraints with the current astrophysical.
Well, at least at the time when we looked at this, well, maybe we missed some papers, which is possible, but this was the stiffest. I'm talking about microscopic calculations, not based on phonological approaches, purely microscopic. I could not find a stiffer. There are some relativistic,
but I do not.
Bruckner, for instance, but they are comparable to what is called the Bob here. So they leads to similar equations of state, as stiff as. So maybe there's so if there is stiffer equation of state, then sure, yeah, we can refit some functionals and see what happens.
Okay, but I do not quite agree that this is a purely microscopical approach which do not have phenomenology inside, because they do have the
yes. Microscopic
so
should be yes, I agree. There is some phenomenology, of course, in these approaches. I mean, only a purely microscopic ab initio would be QCD, but so here there is a phenomenology in the effective potentials between nucleons, and the three-body force is phonological, and so yeah, it's not 100% microscopic. I completely agree.
Yeah.
But it's still in the field. It's still considered as microscopic because it starts from interactions between two nucleons.
Right.
So it is in this sense that it is microscopic, but there is some phenomenology. I fully agree. Yes.
Thank you for clarification.
Okay, more questions?
But I mean, our ultimate goal is actually to rule out the functionals. I mean, because we want to learn some things about physics, so we do not want to keep all these functional at the end. I mean, if we can rule out, well, hopefully we still want to keep at least one, but we want to rule out as many functional. This way, we can really learn what is the symmetry energy, what is the stiffness of the equation of state, and so on. So it's also the ultimate motivation is to rule out as many equation of state as possible, not to keep them.
Yeah. Well, more questions?
May I ask you,
Sure.
Nicola, could you please tell if there some reason to expect that you said that your objective is to describe the dynamics of neutron stars. Is it possible that in dynamical matter some properties which you try to account with so high precision can become unimportant? So in dynamical matter, some things may be not so important in the effort. I can say that it is not needed, this effort, but they may be not so relevant for dynamical matter. For example, magic nucleus, some electron, some levels, populations, and so on.
When I think that when we deal with the dynamics, then one should be very careful with, for instance, instabilities. So in many models, there can be completely spurious instabilities, which may not be seen if one considers just a purely static case. So, but this can be hidden in the models. And this may appear during the dynamics, and this is related to specific parameters, specific parts of the models. So, for instance, I mentioned that for some functionals, we see that above some density, for instance, the matter tends to be, for instance, ferromagnetic, which is not predicted by more microscopic approaches. So this means that it is spurious. So we made sure to adjust the parameters in such a way that such instabilities do not appear. And similarly, if one is not using consistent equations of state or consistent inputs, if one do a matching not very carefully, then there could be also instabilities because of the matching. So now, usually this is not seen, but simply because the spatial resolution, the spatial grids are not very small. So in fact, there is maybe one grid point for the crust, and so. But as the simulations will improve and the spatial resolution becomes smaller, then this kind also of issues will arise. So just simply instabilities. So not even considering more specific data, but just avoiding instabilities. It's already, I think, it may be important for neutron stars. In fact, it is important for atomic nuclei. So this has been tested for atomic nuclei. If you take a random, you pick up some models. And these models contain some instabilities. If you try to solve the DFT equations running enough iterations or with a small enough grid, then you see indeed that just the nuclei just blow up. So it becomes unstable, and you have everything collapse. So you can see this kind of instabilities in also in atomic nuclei.
Yeah. Thank you.
Okay.
But for the dynamics, also the relevant inputs would be inputs related to, for instance, giant resonances in atomic nuclei, related to the dynamics of vibrations of atomic nuclei, or from heavy ion collisions. One can get in this way constraints on the compressibility, on effective masses, which are also important for the dynamics. So there are existing observables to improve this part of the functionals.
Thank you.
Yes. Please, more questions, comments? No questions. Well, if not, then let us thank the speaker again. I like the talk very much because it showed not only the achievements, great achievements, theoretical achievements in this field, but open questions as well. And these open questions are numerous, so there is plenty of work ahead. Thank you.
Well, thank you very much again.
Thank
I
you
was
very
very pleased to
much.
give this. Thank you.
It was a pleasure to see you.
Yeah, for me too. Yes.
Yeah. So the seminar is over. The next seminar will be next week and it will be announced. So goodbye. Thank you very much for everyone who attended this seminar, especially the speaker, of course.
Who will be the next speaker?
Elizabeth Rispayeva.
Ah, Lisa.
Ah,
Cool.
cool. Yes,
Okay.
it's over.
Okay.
Okay, bye-bye.
Bye-bye. Thank you.
Goodbye.